Dear colleagues, let's start. I am Tatiana Говорущенко, Dean of the Information Technologies Faculty of Khmelnytsky National University, Ukraine. I will moderate our section S3.3, Processing, Recognition and Prediction. I wish everyone fruitful work, interesting presentations, and we work from 11:15 till 1 p.m. So we have 105 minutes, and we have 5 presentations for today. So we have 20 minutes for each speaker. Good time limits in my mind. So I ask all speakers to follow this time limit, up to 15 minutes for a presentation and up to 5 minutes for questions, discussion. I would thank you so much. Our first presentation is a lossy compression of noisy medical images by Vladimir Lukin, Sergey Krivenko, Olga Krylova, and Lyudmila Krivenko. Who is speaker?
Dear colleagues, my name is Sergey Krivenko, and I will be a speaker in this section.
Welcome, Sergey.
Can you hear me well?
Yes, we hear you.
Okay,
Welcome.
let's start. Can you see the first slide of presentation?
Yes.
Okay. So, dear colleagues, let me introduce myself. I'm Sergey Krivenko. I'm senior researcher of Department of Information Communication Technologies, and I'm going to represent our recent study, lossy compression of noisy medical images. But before presentation, let me briefly describe who we are and what are our direction of research. Department of Information Communication Technology has more than 40 years experience in digital signal and image processing, with application to color imaging, as well as multi-channel remote sensing data from airborne and spaceborne carriers. The main direction of research are the following: design of visual quality metrics and databases of their verification, lossy compression of grayscale color and multi-channel images with quality control, field design of image denoising and prediction of their efficiency, and the classification of original and pre-processing images. Let me introduce outline of our study. These are: first, introduction; second, used image noise model, compression criteria and techniques. Third, analysis of optimal operation point existence and comparisons. And fourth, conclusion and future work. As we all know, medical imaging systems are widely used in ophthalmology, gastroenterology, dentistry, and other medical applications. Modern sensors produce a huge amount of data due to acquiring a lot of images of a relatively large size. This leads to problems in data storage and transferring via communication lines needed in telemedicine. Then, data compression can be useful. There are numerous techniques of image compression. Lossless and lossy compression methods form two main groups. Although visual lossless approaches can be nowadays treated as an intermediate useful option. lossless image compression is often useless since it produces compression ratio CR, which is only slightly larger than Unity. I mean well-known zip, PNG, and other formats. This happens especially often if an image to be compressed is noisy. Then a lossy image compression approach has to be applied. And we should keep in mind that lossy compression introduces an inevitable distortion that should be taken into account and controlled. Considering the aspect of control, two types of situation are to be studied. The first type of situation relates to lossy compression of images that are practically ideal. I mean noise-free. Then CR compression ratio in case of majority of images results in large distortions and monotonous rate distortion. Sorry for my stuttering. Covers that allows us providing a desired quality in iterative or two-step way for any compression method. The second type of practical situation concerns lossy compression of images that are noisy and noise is visible. Effects deal with specific noise filtering effect due to lossy compression and possible existence of the so-called optimal operation point associated with noise filtering. It might happen that the positive effect of noise removal is larger than negative effect of useful information degradation. And then there is an optimal value of parameter that control compression, PCC. For a given coder, for which the compressed image is the closest to the noise-free one for a given noisy image according to used similarity metric. Existence of OOP has been demonstrated for many coders and noise types as well as for different similarity quality metrics. So, the main goal of the study is to check whether or not the use of AVIF and HEIF modern coders can be expedient in lossy compression of noisy medical images. We have done our analysis for additive white Gaussian noise AVGN, which being a starting point in research of noise filtering and lossy compression of noisy images. And alongside with traditional metrics such as mean squared error and peak signal to noise ratio, MSE and PSNR, visual quality metrics like PSNH-VSM and MSSIM are applied since visual quality of compression medical images has a prime importance. Keeping in mind the aforesaid, the observed image possible after the proper variant stabilize and transform can be represented in this formula. AVGN variance is assumed to have zero mean and variance equals variance equal to sigma squared, which is supposed to known or accurately pre-estimated in advance. We will use 5 coders, JPEG, and 4 modern coders, ADCT, BPG, HEIF, and AVIF. As test data, we have considered 2 512 by 512 pixels images, dental 1 and dental 2. They can be treated as typical examples of medical images where noise is practically invisible. Images of different complexity, where the image dental 2 is more complex and contains more objects and textures. It's known that OP existence depends on image complexity and noise intensity. Keeping this in mind, in simulation, we have considered three values of a VGN variance. The first one is equals to 25, that approximately corresponds to noise visibility threshold for white noise. The second will be 100, that approximately relates to the case of visible noise. The third one will be 196, that corresponds to intensive noise visible in practically all fragments of the images. Let's start from analysis of visual quality metrics, particularly PSNR HVSM, scatter plot on the right side. The main observation is that all colors are monotonous. I mean, PSNR HVSM on QF for JPEG on Q for BPG and on QS for the ADCT coder. This means that OP in this case are not absorbed. It has been met earlier that OPs for visual quality metrics happens less often than for conventional PSNR. Meanwhile, it can be stated that for Q less than 20 for BPG, QS less than 10 for ADCT, and QF more than 70, JPEG, AVIF, and HEIF, compressed image quality practically does not change. Let's consider PSNR on CR case. Analysis of the obtained data for left side scatter plot showed the following. First, CR in OP is the smallest for JPEG, approximately 10, and the largest for AVIF, approximately 50. Second, PSNR in OP is the largest for the ADCT and BPG coders and the smallest for JPEG. Third, if one plans to reach a reasonable trade-off between CR and PSNR, this means to have PSNR close to maximal and CR rather high. This means equal to 40, as you can see. The best option is to use BPG coder without ADCT, AVIF, and HEIF coders provide slightly worse results. Even for CR equal to 50, the compressed image quality is high for modern coders. The analysis of right side scatter plot shows that all values of CR in OP are smallest than 15, and the smallest CR is absorbed for JPEG, approximately 6, and the largest for AVIF, approximately 15. In general, the best results are provided by the BPG coder, although the data for the AVIF, HEIF, and ADCT coders are only slightly worse. For CR approximately equals 20, the compressed data quality is significantly worse than in OP. Thus, the range of appropriate CR values for image compression depends on image complexity. Let's consider the case of variance equals to 100. For the image dental 1, there are obvious OPs for all 5 coders. Minimal value of MSE on PCC are the smallest for the BPG and ADCT coders, although they are only slightly larger than AVIF and HEIF coders. The results for JPEG are clearly the worst. It's worth stressing that position of minima, I mean OP values, have changed compared to the case of sigma square equals to 25. For the dental image to dental 2, OP are also obvious for all considered coders. Minimal values of MSC on PCC are again the smallest for the BPG and ADCT coders, whilst the results are the worst for JPEG. For larger noise variants, OP becomes more probable for visual quality metrics. For the image dental 1, there are OPs for 4 out of 5 coders. The only exception is JPEG, where the best results are provided by the ADCT and the BPG coders. Meanwhile, for the more complex image dental 2, all dependencies are monotonically decreasing, where the best results are again provided by the BPG encoder. Thus, the OP existence depends on image complexity. Finally, let us give some results for sigma squared equals to 196. OP are obvious for all 5 coders. QF in OP move to smaller values for the coders AVIF, HEIF, and JPEG, whilst Q for BPG and QS for the IDCT coder become larger. Minimal MSE on PCC are practically the same for all 4 modern coders. Similarly to dependency in previous slide, all dependencies for dental 2 are monotonically decreasing for all coders except BPG, for which there is a local maximum and the results are the best. During the reviewing process, one of reviewers asked us how can be confirmed truthfulness for the experimental results. To check whether or not the observed dependencies and tendencies are typical for the noisy medical images, we have also tested the true image fragment of middle complexity containment by AVGN with sigma square equals to 100. As one can see, the BPG coder produces a minimal MSE, although OP are observed for all 5 coders according to metric MSE. In this sense, the results for the test image fragments are more similar to the results for the image dental 2 than for the image dental 1. Nevertheless, compression VCR less than 20 can be considered reasonable for 4 coders except of JPEG, for which quality radically reduces if CR increases. The BPG coders is still better compared to the other in wide limits of CR variation, so its benefits is not too large. Well, the conclusion of our study are presented in this slide. The general idea is the obtained data have confirmed the tendencies known for ADCT and BPG coders. And we can state that AVIF and HEIF coders can produce the results slightly worse than the BPG coder. Thank you. One more thing that our future work is presented in this slide, and thank you for your attention and your question, please.
Thank you, dear Sergey. Questions, please, dear colleagues. I have one small question about the detalization of your future directions in for your research.
This one?
Yes. Detailed, please.
As any scientific study, we have some direction which can be done in future, and these directions are threefold. The first question which can arises is can we predict OP existence for the Aviv and Hiv quarters. The second one is which way to determine OP have to be proposed and tested to carry out noisy image compression in OP or its close neighborhood in fully automatic manner. And the third one, the more complex cases of signal dependent and spatially correlated noise have to be studied, because in this study we consider only AVGN case.
Thank you. More questions, please? No more questions. Thank you, Sergey.